Hello and welcome back. In this video, we will continue our discussion on multi-views. In the previous video, we looked at the role of sketching and solid modeling in engineering design, and the various classes of projection that can be used to represent 3D objects graphically. We ended off at isometric pictorials, which enable quick three-dimensional visualization of parts. Since the main goal of isometrics is clarity before detail, isometrics are not intended to be used as dimension working drawings. For this, we need multi-views, which is the topic of this video. Specifically, we will look at the glass box theory and standards to understand how multi-views are arranged, and we will also examine the main line types in multi-view drawings, as well as guidelines for view selection. Recall that multi-views are a subclass of orthographic projection where the projection plane is parallel to a principal face of the object, leading to a two-dimensional view. If we combine multiple multi-view projections of different principal faces, we end up with a collection of 2D views as shown on the previous slide that can clearly be dimensioned to provide a complete and clear description of the product geometry, which is necessary to ensure that it is manufactured as intended. So how do we obtain these 2D views, and how do we arrange them together? We can use the glass box theory to help with this. To generate a multi-view using the glass box theory, imagine a bounding box around an object as shown here. Each face of the bounding box will act as an orthogonal projection plane. An orthogonal projection is drawn onto each face of the bounding box, as seen by an observer outside of the box, which is then unfolded to obtain a multi-view representation. Note that there are 6 principal views: top and bottom, front and rear, and left and right. You can see in this multi-view that the top and bottom views both provide width and depth information, the front and rear views provide height and width information, and the right and left views provide height and depth information. Since these views come in pairs of duplicated information, we typically only need 3 out of the 6 views to completely define the object's geometry. 3 standard views are the top, front, and right views outlined in this box. With this multi-view representation, the key idea here is that each view shows certain definite information with features shown in true size and shape. There are some exceptions to this. For example, oblique surfaces that are not parallel to the projection plane will not be shown in their true size in any of the principal faces, but we'll return to this topic in the next video. For now, let's focus on these 3 views: top, front, and right. Usually, these 3 views are sufficient to completely define a part's geometry, with each view aligned and sharing one dimension with each of the other views. This is shown in the example on the slide through the help of construction lines that connect each of the views together. For instance, the top and front views are aligned vertically and they share the width dimension. The front and right views are aligned horizontally and they share the height dimension. And while the top and right views are not directly aligned, they do share the depth dimension, which can be seen by projecting sight lines through a 45-degree miter line. It is important to note that all of the previous examples shown using the glass box theory are what is called third angle projection. This is the multi-view standard used in North America, named as such because they are generated as if an object is placed in the third quadrant, as shown in the figure to the right, where the views of the object are projected onto the planes in front, on top, and to the right of the object. As seen with the glass box theory, in third angle projection, the projection plane is located between the observer and the object. The International Projection Symbol used in professional engineering drawings, created using this third angle projection standard, is shown here. We will use third angle projection in this course. However, there is one other projection standard to be aware of called first angle projection. In first angle projection, we imagine that an object is placed in the first quadrant between the observer and the projection plane, with the views being projected onto the planes behind the object. This first angle projection standard is commonly used in Europe and Asia, and results in different multi-views than the third angle projection, where the profile left and right views and the horizontal top and bottom views are essentially flipped, which is reflected in its international projection symbol. Again, we will use third angle projection in this course, but it is good to be aware that first angle projections are commonly used outside of North America as well. In any case, you may have noticed a variety of line types being used in multi-view projection examples that we have looked at. 3 main line types used in multi-views are visible lines, hidden lines, and center lines. Visible lines on a multi-view are the solid lines that represent visible edges in a view, while hidden lines are the dashed lines that show hidden features that can't be seen in a particular view. Hidden lines could represent the limiting element of a hole, a hidden change of planes, or a hidden edge of a surface. And to determine what a hidden line represents, you should always relate it to the other views. For instance, we might not know that these hidden lines represent a hole in the top and right views until we look at the front view and see that these correspond to a circular feature in that view, telling us that this is a hole. Another feature that helps us realize that this hidden feature is in fact a hole is the presence of center lines on multi-views. Center lines are dashed lines that alternate between long and short dashes, and these are used to indicate the center axis of a hole feature. On the circular hole face, two crossing center lines are combined with a center mark, and together these annotations also help us identify the hole. And more generally, center lines are used to indicate axes of symmetry, and they can even be used to show a path of motion. These are the main line types that you'll encounter on multi-view drawings, and they do have an order of precedence in case they coincide or overlap in a view. This order of precedence is visible lines first, followed by hidden lines, and then center lines, meaning that if a visible line and a hidden line overlap, or a center line overlaps with a visible line, then the visible line is drawn because it has the highest precedence. If a hidden line and a center line overlap, then the hidden line is drawn. So now that we've covered the glassbox theory and multi-view line types, we should be in pretty good shape for generating multi-view representations of parts, such as the one shown on this slide. What we have yet to discuss, though, is how we should go about selecting the front view, which is obvious in some instances and less obvious in others. For the less obvious cases, perhaps like the one on this slide, there are a few heuristics that can be used to select a front view, with the most important consideration being the selection of a singular view that best describes the overall shape or function of the object. In addition, we usually want the object's longest principal dimension appearing as a horizontal dimension in the front view, and when choosing between two views that outline the same shape, the one with the fewest hidden lines is a preferred view, and that one should be selected as the front view. The reason being is that hidden lines are harder to interpret than visible lines, so we generally want to avoid them when we can. Finally, when selecting a front view, we should also be considering the subsequent arrangement of the top and the right side views, as we generally want to avoid blank space in our overall drawing. So let's consider some example parts for which we want to select the front view. In the example in the top left, between the two views, they both show the same general shape, but the option to the right has fewer hidden lines than the option to the left. For this reason, we'd pick the option to the right. For the car example in the top right, we have three options to choose from, and we want to select the view that provides the best overall shape of our car. So in this case, the left or right options provide the best overall shape, but it's the option to the left that makes the most sense in terms of a car's function with the wheels on the ground, and this also gives the longest principal dimension as the horizontal dimension of our front view, which was one of our heuristics as well. For the example on the bottom, which was the original example that we considered, I would argue that the middle option provides the best overall description of our part's shape, the L-shaped profile, so I would select this one as our front view. Let's consider one more example. Here we have a part and we have 6 options for our front view. So I'd suggest that you pause the video now and try to determine the best option for the front view on your own. Okay, so out of these 6 options, we can see that A and D are similar, B and E are similar, and C and F are similar. So let's try to eliminate one of each. So between A and D, they both provide the same general information about the part's shape, but A has more hidden lines than D, so I'm going to eliminate option A. Between B and E, they both provide the same general information, and they have the same number of hidden lines, so let's just leave those for now. Between options C and F, again, they both provide the same general shape, but option F has more hidden lines, so we'll eliminate that option. Now we're left with B, C, D, and E to choose from, and I'm going to go back to one of our heuristics, which is to select the view that gives the longest principal dimension as the horizontal dimension in our front view. So in options C and D, we have a longer horizontal dimension than in options B and E, so I'm going to eliminate options B and E and just choose between C and D. Between these two views, I would argue that option D provides more detail about the part's shape because we have the rounded features, and we can also see in this view that there are at least 6 holes, whereas in option C, we can only determine that there are at least 4 holes. For this reason, I would select option D as our best option for the front view. Okay, so another guideline related to view selection is to include the minimum number of views that allows for a complete, unambiguous representation of an object. For most objects, 3 views are required to fully document the part, as seen by this multi-view of one of our previous examples. That said, in some cases, only 2 views are needed. This is true for simple parts like washers and bushings, as well as for this T-slotted bar to the right. In fact, we could probably include just a single T-slot profile, along with a note of the bar extrusion length, and that would be sufficient. In other cases, like for parts with much more complex geometries, additional views may be needed, which we will consider in further detail in the following video. Overall, the general rule is to include as many views that are needed to present the object's features, but no more. We want to ensure that the true measurements needed to define all features can be seen in at least one of the views, and that we've provided enough views so that it is impossible for the geometry of any feature to be misinterpreted as another type of geometry. Let's consider another example where we are presented with 2 views. The question is if these 2 views are sufficient to unambiguously define this part, or if we need another view to fully define the part. Looking at these views, we might assume that the part looks something like this, an L-shaped bracket with a rounded top. But we could also assume that the bottom of the bracket is also rounded. These 2 different parts have identical front and right views, which tells us that we need the top view to unambiguously define the part. The reason that these 2 front views look identical in this case is because a straight line in a multi-view can either represent an edge, as seen with the part to the left, or it can represent the limiting element of a curved surface, as seen with the part on the right. So it's important to cross-reference other views to determine whether you're looking at an edge or a limiting element. This just goes to show that when you're creating multi-views, you should always ask yourself, are there enough views included to ensure that it is impossible to misinterpret any part features? So that wraps up our discussion for this video. In this video, we dove into the topics of multi-views, starting with the glass box theory and first and third angle projection standards. We looked at line types and view selection for multi-view generation. And in the next video, we will look at additional views that are sometimes required for more complex geometries, as well as the conventions for annotating and dimensioning multi-views, as shown by the example on this slide. Altogether, this will give us the knowledge required to make professional engineering drawings that provide a complete and clear description of part geometry, which is necessary to ensure that parts are manufactured as intended. Until next time.